when we are going into polar, ideally we want to have theta equals, or r equals, or even sometimes r squared equals if we can't get r by itself. So we are going from rectangular into polar, and the things that you need to get from rectangular into polar are, we know that r is equal to x cosine of my angle, x is equal to r cosine of my angle, and y is equal to r sine my angle, and x squared plus y squared is equal to r squared all day long. So those are the things that you use so that you can put these A and C into polar coordinates. So maybe you've already started the homework, which is cool. On A, I'm going to replace x with r cosine theta. So r cosine theta is equal to 4. And I want it to be r equals, and so all I have to do is divide both sides by cosine theta, and I'm done. If I want to go further and say I don't like to have cosine in the denominator, then I can just use the equivalent reciprocal function. So r is equal to 4 secant of theta. And I personally, if this was on the test, I would accept either answer. So either answer is perfectly acceptable. So any questions on that one? Cool. So on the next one, I've got y squared is equal to 2x. So I'm going to replace y squared with r sine theta squared. So r sine theta squared is equal to 2, and I'm going to replace x with r cosine theta. How are we doing so far? Doing okay? So now I am going to square the r. I'm going to square the sine. And I get r squared sine squared theta is equal to 2r cosine theta. Now I'm trying to solve for r, so what I'm going to do is I'm going to divide both sides by r. When I divide both sides by r, I get r sine squared theta is equal to 2 cosine theta. So all I did was I divided both sides by r. So I'm going to divide this by r and this by r.
How did you get r squared again?
Because I have my replacement for y is r sine theta. Because y is squared, I have to square the r and I have to square the sine of theta. So now all I have to do is divide both sides by sine squared, and so I've got r is equal to 2 cosine theta over sine squared theta. Now I'm perfectly fine with that answer. If you decide that you don't like to have sine in the denominator, then you can rewrite this as r is equal to 2 cosine theta over sine theta times 1 over sine theta. Again, I'm perfectly fine with the previous answer. If you decide to do this, then what you're going to get is r is equal to 2 the cotangent of theta, because that's a replacement for cosine over sine. And then the replacement for sine is cosecant. So again, I'm perfectly fine with this answer, but if you'd like to go further, that is fine too. Yes?
Does web work either one?
It'll take either one.
Oh.
Yep, because they are equivalent. Personally, I am inclined myself, if I was a student, I would probably stay right here, but, you know, that's just me. I just don't want to do a lot of work. All right, any questions on these besides that? Anything else? Okay. Now we're going to graph these. So when we're graphing these, we can make a table of values over 0 to 2 pi, and we can just start plotting these on the polar plane. There are some functions or some equations in the polar plane that will always have the same shape. So if we take a look at our first one, this spiral, we have r is equal to theta. So we're going to plot the points r comma theta, but remember r equals theta, so I'm really plotting theta comma theta. I have to be in radians. So if I have the angle of pi over 6, then that's going to be what my r is. So I would plot the point pi over 6 comma pi over 6. And then I would, when I plot that, I'm going to put that into my calculator and I'm going to get the decimal equivalents. So that's about right here. If I do r is equal to pi, so in other words I'm plotting pi comma pi, so pi is the angle, so here's where the angle is, so it is, the angle pi is right here, but I'm also out that pi distance. So I would continue through, and that's how come I get the spiral as it comes out. Now, all of my equations that are set up with r equals a cosine theta will all be circles in which my diameter is a distance of a, my center here, my center is on the a over 2 comma 0, and my radius is a over 2. If I would have had a less than 0, then what it does to my graph is it just orientates it on the other side of the y-axis. If I have r is equal to a sine theta, then again my diameter is a, my center is located at the point 0 comma a over 2, and my radius is a over 2. That's for a greater than 0. If a is less than 0, then I am orientated on the other side of the y-axis, but I still go out to a, down here would be negative a. My center is going to be at 0 comma negative a over 2. So the next one I have is a 3-leaf rose, where notice that this is no longer theta, it is 3 theta. So 3 theta is my row, or is my angle, and that tells me I have 3 petals, 1, 2, and 3 petals. Also what I know is that the distance between each one of the petals down the midline is going to be 360 divided by 3 because I have 3 petals. So in other words, the distance between the petals is going to be 120 degrees. If I have an a, so that's good for the a greater than 0. If I have a less than 0, then what it does is it starts, my petal will be over here, and then it'll have these other shapes like this. They will still be 120 degrees between them. Now, if I have, r is equal to a sine 3 theta, then I still have 3 petals, but now it looks like this. And this is for a greater than 0. If I have a less than 0, then it's going to look like this. Now, let's look at the r cosine 2 theta. So if I have r is equal to a cosine 2 theta, I still got a distance a. My leaf length is a, and minus a and minus a. But notice this is 2 theta, but I actually have 4 leaves. If I would have had r is equal to a cosine 4 theta, then I'm going to have actually 8 leaves, where I've got 1, 2, 3, 4, 5, 6, 7, 8. And these look so much better if you do these on Desmos. Mine are actually pretty awful. If you were to graph these in Desmos, right here, these actually should not overlap, but my drawings are just delicious. So anyways, that's what our cosine, if you have our cosine for theta. If you have 8 theta, that means you're going to have 16 petals. So for odd numbers, if we look back over here, for odd numbers, if I have an odd multiplier, then that's just going to be that many petals. But if I have an even multiplier, like over here, then it's actually 2 times. Now, if I have a negative out front of this, it's not going to change. So what I mean by negative out front, this is for a is greater than 0, but also if a is less than 0. And that's because cosine is even. It's not going to change the directionality. However, if I had, let me see, let me erase this. Let me erase this. If I have sine, so if I'm looking at r is equal to a sine 2 theta, then it's going to look like this, where I have this, and again, that's some great drawings. So the radius still, however, it still has a radius of a. In other words, the length of the petal is still a. It's just orientated differently. And then if I have, let me erase this. If I would have had r is equal to a sine 4 theta, then I'm going to have 4 petals. 1, 2, 3, 4, 5, 6, 7, 8. I'll have, 8 petals. And so it's going to look something like that. And this is the lemniscape. And what I look for the pattern recognition is I have r squared. Now if I have r squared is equal to a sine 2 theta, then what it will look like is, it will look like this. It'll still have that propeller shape, but it's going to be facing up and down. So that's a lemniscate. So let's look at our last couple of shapes. We have a rose, a 3-leaf rose. Notice that we have a, and then I have 1 minus cosine theta. But that's not a 3-leaf rose. That's a cardioid. And that's not a 3-leaf rose. That just must have been coming over from the previous page. This is a cardioid. Now, if I have r is equal to 1 plus the cosine theta, and my a is out front, then what it does is it reverses the shape of my cardioid. If I have r is equal to a 1 minus the sine of theta, then it's going to be orientated in this direction. Notice that for both of these, whether I have positive cosine or negative cosine theta, that I'm going to go out a distance a on the y-axis and a distance 2a on the x-axis from the origin. And the same thing is going to be true as if I have r is equal to a 1 minus sine theta. And again, if this would have been a 1 plus sine theta, then I'll be orientated in this direction, like that. Now, a limison is basically just looking a lot like a cardioid, but it has a little loop in there. And the difference between a cardioid and a limison is that this constant and this coefficient are not the same values. Now, if my A value happens to be less than my B value, then I end up with this loop. So again, if my A value is less than my B value, then I end up with a loop. If I have an A value is greater than the B value, then I still have the same kind of shape, but that loop that I had before, like that, is now gone. So I still go out on the limison, the limison, it's not a limescate. When we have a limison, I'm still going to go out a distance of A, but the difference that is here is, notice this goes out A, this goes out negative A, but this from the origin is A minus B, and then from the origin on this side is the negative A plus B, right? So if I'm asked to sketch the polar equations, then I ask myself, does any of these match the shapes that I already know? So I have r is equal to 2 sine theta, and that looks like a circle. So if I go back up here, and that looks like it's a circle, so let's see if that's a circle. And it is indeed a circle. It actually matches this equation type right here, so it's a circle. So this is going to be a circle in which my radius is going to be half of A, where this is A. So my radius is going to be 1, and I know from the origin to the other side is 2. On the next one, I'm looking to see if that matches anything that I know from up above. So clearly it's not a circle, but it looks like it might be a cardioid. And in fact, it's this cardioid. So I know that this one, B, is going to have a shape of a cardioid in which I am going in the opposite direction, where my A is 1. So the edge of my cardioid is at 2 times 1, and then I go down 1 and I go up 1 because that is my cardioid. This one here we know is going to be a rose. So it's a rose where I take whatever that theta is, and in this case it's, the multiplier 2 theta, and that's going to tell me I have a rose with 4 leaves. So 1, 2, 3, oh, sorry, got wild with my leaves. 1, 2, 3, 4, where the length of my leaf is 3. And then lastly, I have this shape. With this shape, what I have is either a limison with a loop or a limison without a loop. So I either have this one or I have this one. It's one or the other of these. So I come back and I say, okay, well, A is 1, B is 2. So if A is 1 and B is 2, it actually is a limison with a loop in it. And because it should be a minus, but mine has a plus, that means that I have a limison in this direction. It looks like that. All right, so for the very last part of this section is we're trying to find the exact coordinates of these polar equations where they intersect. So if I have 2 equations, 2 unknowns, my first choice is to set one equal to the other if I can use substitution. So because I have r is equal to 3 cosine theta, and r is also equal to 1 plus the cosine theta, I'm going to set them equal to each other and solve. I have cosines on both sides, so I'm going to subtract cosine theta from both sides. So they get them on one side. And so I have 2, the cosine theta is equal to 1. The cosine theta is equal to 1/2. So I look on my unit circle to see where the cosine theta is equal to 1/2. Cosine theta is equal to 1/2 at pi over 3 plus 2 pi k. And when theta is equal to 5 pi over 3 plus 2 pi k. So that's my two solutions. On this one right here, on B, I am going to do a substitution again. I'm going to replace r squared with the square root of 2. So I have the square root of 2 squared is equal to 4 cosine 2 theta. So 2 is equal to 4 cosine 2 theta. I divide both sides by 4, so I get 1/2 is equal to the cosine 2 theta. And I ask myself, where does the cosine equal to 1/2? Well, again, that's at pi over 3 plus 2 pi k, and also at 5 pi over 3 plus 2 pi k. But I'm solving for theta, not 2 theta. So that means I'm going to divide both sides by that 2. So I'm going to divide this by 2, I'm going to divide this by 2, and when I'm dividing by 2, that's the same thing as multiplying by 1/2. So theta is equal to pi over 6 plus pi k. I'm going to do something similar to this equation, so I get theta is equal to 5 pi over 6 plus pi k. So those are my solutions for that one. All right, so now let's do this last one here. So again, I'm going to do substitution. 1 is equal to 2 sine 2 theta. Divide both sides by 2. So 1/2 is equal to the sine of 2 theta. And I ask where the 2 theta, in other words, where my angle is equal to 1/2 on the unit circle. That happens at pi over 6 plus 2 pi k. And it happens at 5 pi over 6 plus 2 pi k. Now I divide everything by 2, just like I did before. Divide by 2 or multiply by 1/2. So I have theta is equal to pi over 12 plus pi k. And similarly, theta is equal to 5 pi over 12 plus pi k. So those are my final answers, and this finishes 11.4 and 11.5.